So we want to look at some problems involving multiple roots and some other types of problems involving roots of an equation. So the first one here is that if alpha is a double root of the polynomial, show that alpha is a zero derivative of the polynomial. Well, that's the proof that we had before. So we've got the situation here. If we've got a double root, we know that x minus alpha all squared times qx, where qx is a polynomial, would be equal to px. So this is going to, because it's a factor. So deriving, we've used the product rule, and on the we use the chain rule on this one. So the 2x minus alpha times 1 times qx, and then the first function times the derivative of qx, which we don't know what it is, but we don't really have too many hassles with what it is. Factorise x minus alpha out, and leaves us 2qx plus x minus alpha q dash x, which means that x minus alpha is a factor there. So when derivative is equal to 0, then x minus alpha is a root of the derivative there. So that's how that one works. So the idea here, can we apply it to find a and b in this polynomial, given that x minus 1 all squared is a factor? There's a factor there. So what does that mean for us? Well, when we substitute 1 in, so x minus 1 all squared, we substitute the 1 in, we substitute it in, and it's equal to 0, we're able to set up an equation as a is equal to minus 3 minus b. So we get a relationship between a and b. If we can get another relationship, then we can solve them simultaneously. So the derivative of x is that function, and then when we sub 1 in, we get that 3a minus 2b minus is equal to minus 13. Thus, because a is equal to minus 3 minus b, we can substitute that in, and then we can solve for b, and then we can substitute back in for a. So it allows us to solve that because we know it's a double root, so the derivative as well as the function itself must be equal to 0 when x is equal to 1. So in this problem here, the first part basically asks us to prove the idea of roots occurring in complex conjugate pairs. So alpha and conjugate of alpha, given this situation, would be a quadratic factor of px. If px is a polynomial with real coefficients, and alpha was a non-real 0, then the conjugate would also be a 0. So that's what we want to prove. We've worked with it before, but here's one of the proofs. We're going to prove it again in another way later on. But what we're looking at is the ideas of the properties of conjugates. So if alpha is a plus ib, so it's some complex number there, and it's a non-real 0 of polynomial where we've got an x to the power of n, another coefficient times x to the power of n minus 1, down to a constant. Then we would have this situation. Now, we should note as well that an minus 1 and a0, they're all real numbers, so they're not complex at all. So that means we can do this situation and look at if we have that being equal to 0, because alpha's a root, so we can sub it in for the values there and get it equal to 0. Then if we take the conjugate of that, of both sides, the conjugate of the left-hand side would equal the conjugate of 0, and the conjugate of 0 is 0. Which means that, well, because we've got the conjugate of all these separate terms, we know by our properties that the conjugate of the sum of two complex numbers would be equal to the sum of the conjugates of those complex numbers. So we can split them up. Which means as well that we know when we multiply a conjugate number by a real number, that really it's just the real number times the conjugate of the complex number, so we can split that up as well. And then we know when we've got a complex number to the power of something, and take the conjugate of that, it's really the same as the conjugate of that complex number all to the power. So what we've done is basically used our properties of conjugates to break down and get that we can put this expression in the form where we've got the coefficient times the conjugate of alpha times to the power of the number all the way through, and it's going to be equal to 0, so therefore the conjugate of alpha is also a root. So there's one way to prove it. As I said, we'll prove it another way later on. So having done that, show that x squared plus 1 is a factor of that polynomial. So and then factorize it. So what we want to do is, well, probably the easiest way is to do it with polynomial division here. You might have another way you particularly like to do it. I've done it with division, so and just seeing that it works. So x squared goes into x to the power of 6, x to the power of 4 times. So we get x squared, so the x to the power of 4 times x squared is the x to the power of 6. X to the power of 4 times 1 gives me x to the power of 4. Those terms cancel. So I've got no x to the power of 4 term. Bring the x squared down, and x squared goes into x squared once. And 1 times 1 gives us 1. So, and that starts to cancel out. It comes up with a remainder of 0, so it is a factor. So what does it look like? Well, x squared plus 1, x squared, x to the power of 4 plus 1. They're irreducible. They can't be broken down in the rational field. It would have to go to complex numbers from this. So we can't do it any further. So that's as simplified as we get in the rational field. In question 3 here, we've got find the integers m and n such that x plus 1 all squared is a factor of that one. So again, we're looking at the idea that we substitute minus 1, we substitute that in, and that's going to be equal to 0 because it's a factor. If it's a factor of that, then minus 1's a root. So we put that in, we get m minus n is equal to 1. And then when we differentiate it, because if x plus 1 is all squared, it's a factor, it must be a double root. So for the derivative of minus 1 would equal 0 as well, which leaves us to get m being equal to minus 1 when we solve this equation. And we put minus 1 back in, we get n is equal to minus 2. And we've solved it, and we've got our values. So we start to see some applications of the ideas of multiple roots and how we can use them to solve some problems.